The title of this lecture is Depth Dose Profiling for Light-Ion Teletherapy. With light-ion beams, depth dose profiling is often performed using range modulation. The objectives for this lecture are to describe the concept of depth dose profiling for light-ion beam teletherapy, introduce various parameters associated with energy, range, and range modulation, and describe various methods of generating different depth dose profiles. This slide provides a short list of general references concerning light-ion teletherapy. This slide shows the distribution of dose with depth for a typical monoenergetic proton beam entering a water phantom. Only a small part of the phantom receives a high dose. The part of this distribution is called the peak. Most targets within a patient, such as a tumor, have a dimension in a depth direction much larger than the width of the peak. Obviously, a single energy ion beam cannot adequately treat most tumors without delivering a large dose to surrounding normal tissue. Let us use a simple model of how a finite-sized target could be treated with an ion beam. This slide shows an ideal dose distribution for a target located from 7.5 to 15 centimeters of water equivalent depth within a patient. We would like to have 100% of the prescribed dose within the target and absolutely no dose outside of the target. This ideal dose distribution is represented by the gray box. Let us now superimpose an ion beam depth dose distribution onto the target. The red curve represents a simplified depth dose distribution for an ion beam that has a relatively low but non-zero dose entering the patient and then a high peak dose just before the ions stop. One can see that only the distal 20% of the target receives an adequate dose. In this graph, a second identical beam, shown in green, enters the patient, but since some of the target has already been treated, this beam will deliver only 70% of the dose that the first beam delivered. If we place 1.5 cm of water equivalent material in front of the patient when we deliver the second beam, we can shift the depth of penetration of the ions. This process is called range shifting. This delivers the peak dose at a depth shallower than did the first beam. When we add the two dose distributions together, we see that now 40% of the target receives the prescribed dose instead of the 20% that the single energy covered. We can repeat this process with the third beam shown in blue. Since we have already delivered some dose to the upstream part of the target, we need to reduce the dose delivered by the additional beam. This time we use only 49% of the dose delivered by the first beam. When we range shift this third beam and add the dose to that delivered by the first two beams, we find that 60% of the target is now covered by the prescribed dose. A fourth beam can be added with 6 centimeters of water equivalent shift and with 34% of the dose. This beam is shown in magenta color. When the dose of this beam is added to those of the first three beams, then 80% of the target is covered with the prescribed dose. Finally, we can add a fifth beam with 7.5 cm of range shift and 24% of the dose. This beam is shown in cyan color. When the dose from this beam is shifted and added to that of the first four beams, we see that the entire target receives the full prescribed dose. Unfortunately, we also see that the dose to the patient's surface has risen from only 30% of the prescribed dose when only one beam was used to 83% of the prescribed dose when all 5 beams are used. Deeper than the target, however, the dose remains at 0. The numbers shown above the peak dose of each beam can be thought of as the percentage time each beam with a different amount of range shift was turned on relative to the time the beam with no range shift was turned on. In radiation teletherapy, beams are usually monitored by radiation detectors placed in the beam path, and the relative weights are given in monitor units. In this slide, the number of monitor units have been normalized such that the sum of the monitor units for all beams equals 100. This slide shows more realistic depth dose distributions for several range-shifted beams and the sum dose distribution. Generally, the determination of the relative monitor units for each range-shifted beam requires an iterative optimization process. The relatively flat high-dose region of the sun dose distribution is called the mesa, and the somewhat flat region at shallow depths is called the plateau region. This picture shows some geological landforms commonly found in the southwestern United States where heavy charge particle therapy began with light ion and pion beams. In English, the definition of a mesa is an area of high land with a flat top and two or more steep cliff-like sides. In Spanish, the term mesa means table. In English, the word plateau is defined as an elevated, comparatively level expanse of land. The term derives from flat, plate, or platter in French. There are several parameters that are used to characterize the depth dose distribution. The most common parameter to describe the depth of penetration of a range-modulated portal to a patient is the prescribed range. Historically, this has coincided with the depth where 90% of the prescribed dose is delivered distal to the target. The rationale for this value is presented in another lecture concerning prescriptions. For dosimetry purposes, the dosimetric range is used, which coincides with the depth where 10% of the prescribed dose is delivered distal to the target. Another dosimetric parameter is the residual range that is defined as the difference in depths between the dosimetric range and the depth of measurement. Another parameter that is sometimes used is the nominal center of mesa depth. This value is calculated by subtracting half of the designed 90% to 90% mesa width from the prescribed range. This table provides detailed definitions of several range parameters. The beam range, as described in another lecture, is defined as a depth that corresponds to 50% of the non-attenuated primary eye influence, or the depth that corresponds to approximately 80% of the peak dose of the non-modulated beam. The dosimetric or practical range is defined as that depth that corresponds to 10% of the center of mesa or peak dose. The residual range is defined as the difference between a point of interest depth and a depth that corresponds to 10% of the center of mesa or peak dose. The prescribed range is defined as a depth that corresponds to 90% of the center of mesa dose. Lastly, the delivered range is defined as the prescribed range plus the water equivalent thickness of the range shifter plus the water equivalent thickness of the bolus. Numerical parameterization of the mesa width in a depth direction historically used the difference in water equivalent depths between the depth where the dose at the proximal end of the mesa was 90% of the dose at the nominal center of mesa depth, and the depth where the dose at the distal end of the mesa was 90% of the dose at the nominal center of the mesa. This value is problematic for several reasons. First, if the desired dose to the surface of the patient is greater than 90%, the mesa width is undefined. Second, some institutions chose a defining value different than 90%. Third, for beams of light ions heavier than protons, the physical dose at the distal edge of the mesa, see the carbon ion dose distribution on the right, is typically less than 90% of the nominal center of mesa dose because of a relative biological effect that increases with depth. Fourth, for range modulation techniques that use beam gating with rotating propellers or beam flux modulation with rotating propellers, as will be described later, the mesa width can vary slightly day to day due to system variations. The DICOM communication standard bypassed these problems by specifying conceptual settings for the range modulator or range shifter that are transmitted from the treatment planning system to the beam delivery system. The International Electrotechnical Commission confronted the numerical parameterization problem by defining, for range modulated portals, the nominal range modulation width, or NRMW, as simply the difference in light ion beam ranges for the highest and lowest energy per nucleon components, as given in the equation shown at the bottom of the screen, where LIBRHEN is the light ion beam range for the highest energy per nucleon component, and LIBRLEN is the light ion beam range for the lowest energy per nucleon component. The 90% to 90% mesa width, or MW9090, for a flat biologically weighted dose distribution between the proximal and distal 90% doses may be approximated using the nominal range modulation width in a formulation shown at the bottom of the screen, but measurements should be performed to obtain exact values of the coefficients for different range modulation techniques. On this slide, the difference in depths between the highest and lowest energy components is given by the thickness of a physical range modulation device inserted into the beamline. It should be noted that range modulation techniques that use an upstream rotating modulator propeller, to be discussed later, tend to have a shallower proximal slope than found for range modulation techniques that use energy stacking or downstream located propellers, and thus the relationship may not be valid. Most newer light ion beam facilities use energy influence modulation techniques that allow for different nominal range modulation widths along different fan lines from the virtual source through the patient at different off-axis distances. So use of the nominal range modulation width and meso width parameters may become infrequent as these techniques become more popular. We have now shown that range modulation is a method of depth dose profiling to deliver an adequate dose to a finite-sized target within a patient. There are several different methods of range modulation, and in fact, different methods can be combined. This diagram gives a hierarchy of different range modulation techniques. On the right, within red boxes, are listed several programmable methods including energy stacking, range shifting, beam gating, and beam current modulation. On the left, within blue boxes, are listed methods that employ physical devices. At the extreme left are devices that can provide a uniform dose over the entire target, also referred to as full modulation. On the right branch of the physical devices are so-called miniature devices that only provide partial modulation. The most common of these devices are ripple filters, but not all miniature devices are ripple filters. It should be noted that programmable methods of range modulation may be combined with physical methods. For example, beam gating and beam current modulation are often used with spinning propellers. Similarly, energy stacking and range shifting are often used with miniature range modulators. Energy stacking is a technique where ions of multiple energies are directly extracted from the accelerator to cover a target within a patient with the prescribed dose. It requires the accelerator and switch yard to be retuned quickly and accurately. This technique could not be used effectively until laminated magnets, stable power supplies, and sophisticated computer controls became available during the 1990s. This technique has since, for example, been implemented by Hitachi and Siemens with synchrotron accelerators. Range modulation may also be achieved by inserting so-called range shifter devices into the beam path. These devices may be installed near the accelerator, such as done by IBA and Varian, near the entrance of the gantry, as was done at the Indiana University cyclotron facility, or in the radiation head near the patient, such as done by Mevion. Range shifter devices come in a variety of types, which will be described in the following slides. Before describing the different types of range shifter devices, there is some nomenclature to be discussed. From the 1970s through the 1990s, there were several different names used for slabs of materials inserted into the beam path of radiation treatment beams. One such name was an energy degrader, but the word degrade implied a decrease in quality rather than simply decreasing the energy. No patient would want to be treated with a degraded beam. The term energy absorber was also used on occasion. However, this emphasizes energy deposition with the slab rather than the depth of penetration within a patient. The term decelerator was also used, but this word implied some elaborate electromagnetic process of reducing the energy, so this term fell out of favor. The DICOM Standards Committee chose to use the term range shifter for this type of device. The IEC Standards Committee followed the DICOM choice and defined a range shifter as a range-modifying device that has a constant thickness at all positions lateral to the central axis of the beam. A related issue concerns where the energy should be defined. Several possibilities exist, including at the exit of the accelerator, after passing through a range shifter located near the accelerator, after passing through a range shifter located at the upstream end of the radiation head, or after passing through a range shifter located downstream of the radiation head next to the patient. Both DICOM and IEC have defined the energy as being the energy of ions entering the radiation head. One of the earliest range shifter types is the fluid range shifter. Shown here is the method used at the Harvard Cyclotron Laboratory for radiosurgery. In this system, a beam applicator was used which consisted of a sealed inner cone which held the portal-specific conformal aperture, an open outer cone which slid over the inner cone, and a water balloon which created a flexible membrane to contain the water between the two cones. A single proton energy was used with the initial position of the inner cone and aperture being determined by calculating the necessary water thickness to be held between the cones to irradiate the deepest part of the target. This thickness was calculated by subtracting the water equivalent thickness of the patient from the surface to the distal side of the target from the range of the beam. Once the dose from the deepest range component had been delivered, the inner cone was retracted to increase the water content between the aperture and patient and create a second range component. This process was then repeated until the target was covered with a uniform dose. Another example of a fluid range shifter was used with the pion beam at Los Alamos. In this system, a simple bellows filled with oil was placed in the beam path just before entering the patient. A more common type of range shifter consists of multiple discrete slabs. This picture shows slabs mounted in a carousel that can be automatically rotated to different positions according to the treatment plan. Each hole of the carousel contains a range shifter of a different thickness. When transferring the data from the treatment planning system to the delivery system via the DICOM standard, the thickness setting can be encoded as either the carousel position or the physical thickness. This picture shows another discrete slab range shifter. For this device, a wheel, track, and slab thickness combination are automatically inserted into the beam path based upon the DICOM plan. When modulated scanning is used, generally only the outside track of the lower right wheel is used due to the spot size. The DICOM thickness setting can be encoded as either the physical thickness or a combination of wheel, track, and step number, depending on an agreement between the planning system and the delivery system. This picture shows a device called a binary range shifter that consists of a series of plastic plates with different thicknesses. By selecting different combinations of just a few plates of different thicknesses, a large number of different total thicknesses can be achieved. In the DICOM standard, the total thickness specified by the plan can be encoded either as a single value or as a series of ones and zeros. For a finer selection of different thicknesses, a pair of wedges placed in opposite orientations can be inserted into the beam path. By sliding the wedges in opposite directions, a continuously variable thickness can be achieved. The thickness change can also be made quite rapidly. The use of low atomic number material, such as beryllium, can reduce scatter by the wedges and maintain a small spot size, thereby reducing beam loss during transport. A variation on the dual linear wedge type is to split the wedges into multiple components. This means that the length of the wedges can be less, but the accuracy of positioning must be greater. Another variation of the dual wedge type is to wrap one of the wedges circularly around a central rotation axis. This reduces the largest dimension of the device. In this case, most of the range shifting is done by only the spiral wedge, and a small non-moving wedge compensates for the spiral wedge shape. The DICOM setting parameter for transmitting the thickness from the planning system to the delivery system can be either the rotational angle or the physical thickness. The device shown in this picture was used for a dedicated eye treatment beamline, where the beam spot passing through the wedge, placed at the upstream end of the radiation head, was only a few millimeters in diameter. This picture shows a different spiral wedge range shifter. In this case, the wedge is placed near the accelerator and made of carbon, a low atomic number material to reduce scattering and beam loss. The orange-colored line shows the path of the beam, and the magenta arrow points to the spiral carbon wedge. In the past, delivering one energy at a time, either by changing accelerator energy or by inserting physical range shifters, was considered too slow for many treatments. Two general techniques for range modulation were therefore developed and widely implemented. The first was to quickly rotate an array of range shifter steps. The second was to insert a non-moving array of range shifter steps. These two techniques yield a depth dose profile that is non-varying with off-axis position and is thus called fixed range modulation. This slide shows a rotating range modulator that is located at the entrance end of the radiation head. For each different desired mesa width, a separate device must be installed by hand. This particular device was 11 centimeters in diameter and rotated at a speed of 611 RPM, which is a prime number to avoid any aliasing with 60 Hz noise or its harmonics in the accelerator that may affect the beam current. At the entrance of the radiation head, the beam spot diameter is small, as evidenced by the brown radiation damage to the polycarbonate range steps. This particular device was designed for low-energy proton beams used for eye treatments, and, due to scatter, each device works only over a small range of energies, about plus or minus 4 MeV. These devices are often called propellers because of the resemblance to boat propellers. This slide shows a similar device located at the entrance of the radiation head. It is likewise installed by hand, works with a small beam spot diameter, and works over a small range of energies. This device was designed for high-energy proton beams. Unlike the previous device that works for only a small mesa width, this device is designed for full range modulation, but beam gating can be used to turn the beam on and off over particular step thicknesses to provide partial modulation. This technique does, however, waste some of the ions that were accelerated. Another aspect of this device is that the dose gradient on the proximal side of the mesa may be shallower than with other methods. This picture shows a large propeller that is installed near the middle of the radiation head and intercepts the beam after its size has been spread laterally. This particular device is 43 centimeters in diameter and spins at a rotational velocity of 311 RPM. Like the previous two examples, it is inserted by hand. Due to the large diameter and weight, there is an outside rim to hold everything together, so it is sometimes called a wheel. This particular device was designed for protons at 155 MeV, but works over a range from 120 to 250 MeV. Each mesa width requires a different device. The device seen in this picture is similar to the previous one and is located near the middle of the radiation head and can be used with large beam diameters. Unlike the previous example, it is designed for full range modulation. By placing fully stopping copper blocks of different angular widths over the plastic steps, different mesa widths may be obtained. Unfortunately, many ions are thrown away in this process, reducing the average dose rate and producing stray neutrons. This slide shows the same picture of a range shifting device that was shown earlier, but here it is used in a different manner. In this case, instead of selecting a circular track with large steps, a track with many small steps is chosen, and the wheel is spun at a large velocity. To compensate for the change in scatter at different incident energies, the incident beam current is rapidly modulated to match different step numbers. A different type of range modulator is the so-called linear ridge filter. This method was used at the old Berkeley laboratory and most of the Japanese facilities. The main advantage of linear ridge filters is that they deliver the same depth dose distribution at all times during the treatment and are therefore less sensitive to patient motion or fluctuations in the beam delivery. They are typically located midway between the lateral spreading device and the patient. They are usually made of a high-density material to minimize their thickness and a medium atomic number to scatter ions and blur the effect of the thick ridges and thin valleys. This slide shows various ridge filters made of aluminum and copper. This slide shows a two-dimensional slide exchanger that allows multiple linear ridge filters to simultaneously be installed into the radiation head. According to the treatment plan, one filter may be automatically selected and moved into the beam path. A variation on a linear ridge filter is a spiral ridge filter. This device is constructed by winding a plastic film with a modulated thickness profile around a central plug. The plane of the film is oriented parallel to the direction of the ion beam. The thin film yields a fine lateral spatial resolution. This type of device is useful for small fields needing a high dose rate. A device that can be used for small radiosurgical applications is a conical range modulator. As seen in this picture, it is circularly symmetric, but, unlike the ridge filters, the thickness modulation pattern is not repeated. This type of device is placed at the entrance to the radiation head where the beam spot is small. The use of this device requires accurate beam alignment and device alignment. Linear ridges and circular cones are not the only designs that can be used for static fixed range modulators. This slide shows a design for a multiple pyramid modulator. The advantages of this design are that square pyramids are easier to design and build than circular cones, and they are amenable to 3D printing. Disadvantages are that the resolution is limited to the size of the 3D printer spot. Pyramid filters, like linear ridge filters, must be located far enough upstream from the patient to allow scatter to blur the lateral dose distribution from the thick pyramids and thin valleys. With the advent of 3D printing, range modulators may be made in-house. A favored 3D printing technique is stereolithography. This technique yields a more robust product than some other forms of 3D printing, but it is very slow. In this technique, a container of liquid polymer rosin is scanned by laser one thin layer at a time, generating crosslinks. This movie shows a scanning laser beam moving across the liquid for the printer shown in the previous slide. The maximum size that can be made with this device is 450 millimeters long by 450 millimeters wide by 350 millimeters high. The laser spot size diameter is 120 microns, and the layer thickness is between 0.05 millimeters and 0.2 millimeters. This slide is an example of a stereolithography manufactured pyramid modulator. The device creates a 10 millimeter mesa width that is suitable for eye and radiosurgical applications. This graph shows the measured depth dose of this in-house built modulator. The area weights of each thickness step are given in the upper right corner. As stated previously, one of the limitations is the minimum laser spot size, which makes it difficult to achieve a dose distribution that is perfectly uniform with respect to depth. During the early 1980s, before modulated scanning became available, the Japanese proposed combining a scattering system, a fluid range shifter, a multi-leaf collimator, and a bolus to conform the dose distribution to the target volume. The picture on the right shows ISO range curves where the distal 90% dose would be located for each of the individual range shifter steps. One problem that can occur with energy stacking is if the energy to energy interval is too large compared to the width of the single energy dose distribution peak. In this case, ripples will appear in the composite dose distribution. An example of these ripples is seen in the graph on the left. A so-called ripple filter can be designed and inserted into the beam path to physically generate additional energies spaced closely together and delivered simultaneously, effectively making the width of the peak larger and reducing the ripple as seen in the modified dose distributions on the right. This picture shows an example of a ripple filter. This device was used with a propeller-type range modulator designed for 155 MeV protons, but used at a lower energy of 120 MeV where the peak is narrower. The device consisted of a thin aluminum plate with slots to deliver a second energy over a fraction of the beam area, effectively increasing the width of the single energy depth dose peak distribution. When used in combination with the rotating propeller, the ripple in a dose distribution covering the target was reduced. Another example of a ripple filter uses a technique similar to a standard linear ridge filter, except only a few range shifter thicknesses are used. The picture at the left is a close-up view of several of the individual ridges made with stereolithography. The picture at the right shows the filter, designed for a field size of 200 millimeters by 200 millimeters, installed into a frame that is inserted into a beam applicator. The last range modulator concept to show was born from the desire to reduce the dose delivered proximal to the target and to reduce the number of energies, thereby reducing beam delivery time and patient motion. It was proposed to design miniature ridge filters to generate peak widths ranging from 6 to 20 millimeters. During delivery, a different field size and shape was used for each of the multiple energies. This table provides advantages and disadvantages for each of the range modulation techniques. For energy stacking done at the accelerator, advantages include no extra neutron generation or activation of the beam distribution system, a small lateral penumbra, and variable modulation laterally. Disadvantages include the need for accelerator retuning, need for beam distribution system retuning, adjustment of the scatterers, and a sensitivity to patient motion. When using range shifters located at the accelerator exit, advantages include no accelerator retuning, a small penumbra, and variable modulation laterally. Disadvantages include extra neutron generation and activation of the beam distribution system, lower dose rates at lower energies, a need for retuning the beam distribution system, adjustment of the scatterers, and sensitivity to patient motion. When using range shifters located at the entrance to the radiation head, advantages include no accelerator retuning, no beam distribution system retuning, small penumbra, and variable modulation laterally. Disadvantages include the need for scatterer adjustment and a sensitivity to patient motion. When using range shifters located at the exit of the radiation head, advantages include no accelerator retuning, no extra neutron generation, no scatterer adjustment, and variable modulation laterally. Disadvantages include increased penumbra, microphonics affecting the dosimetry system, and sensitivity to patient motion. When using propellers at the radiation head entrance, advantages are that they are small, can be automatically inserted, and can yield a small lateral penumbra. Disadvantages include a complex design to compensate for upstream scattering, a small energy range, and a constant modulation laterally. When using propellers near the middle of the radiation head, advantages are that they are easy to make, no scatter adjustments are necessary, they work over a wide range of energies, and they are time independent. Disadvantages are that they must be installed by hand, are easy to break, and have a constant modulation laterally. When using full static modulators placed near the middle of the radiation head, advantages are that they are time independent. Disadvantages are that they are difficult to make, have limited field sizes, and have a constant modulation laterally. When modulated scanning and energy stacking became routine beam delivery techniques, the use of physical range modulators and boluses diminished greatly. Research on ultra-high dose rate radiotherapy has, however, rekindled the thought of using these devices to reduce the number of required energies and reduce the treatment time. The graphs at the left below plot calculated dose distributions for a monoenergetic beam with and without a bolus. The picture on the right below is a 3D printed bolus used to produce the range modulation. To summarize, there are many different solutions to provide depth dose profiling. Different devices may be placed at different locations between the source of ions and the patient. Several range and range modulation parameters are used to describe the beam and depth dose characteristics.